Welcome back, everyone, to the third lecture in the eCHT mini course. Nat, take it away.
Thank you. And it's good to see so many people still here. Today the goal is to talk about Burnside rings. But before I do that, just want to say one thing. Last time we ended by talking about power operations on representation rings. And there's a third object in global algebra that discussion points us towards, which is the notion of a global power functor. A global power functor is a global green functor equipped with power operations from the value at g to the value of g at g raised sigma m for each m. And these need to be compatible in basically the ways that we described for the representation ring last time. So that's yet another object in global algebra that's going to be important to us as we go forward. So there's two kinds, these are two kinds of multiplicative structures that you could ask for on a global Mackey functor. One is a global green functor, but another one is a global power functor, which is even more. And as we jump into Burnside rings today, my goal is to sort of speed run the parts of it that are very similar to the representation ring case and try to put an emphasis on the parts that are different from the representation ring case. So that's my goal today. Um, what is a Burnside ring? So G is still a finite group. And for our purposes today, a G set is a finite set X equipped with an action of G. And if I have two G sets, X and Y, we can form the disjoint union, in which G acts the way that you expect, and the product, in which G acts diagonally. G acts diagonally. So that's very similar to what happens in the representation ring case. And using these, we can define an addition and a multiplication on isomorphism classes of G sets. So use these to define plus and times on isomorphism classes of G sets. In this situation, the additive identity is given by the empty G set, and the multiplicative identity is given by the single point with the only G action that it has. Um, and so since we have this structure, once again, we can throw in the additive inverses that are missing to turn this into a commutative ring. And this gives us a ring A of G. This is the Grothendieck ring of isomorphism classes of G sets under the plus and times described above. And this thing arises from the equivariant sphere spectrum. So this is pi naught of the G equivariant sphere spectrum. So that's the connection to equivariant homotopy theory here. From that perspective, this is a reasonably fundamental object. And I'm going to explain more ways in which it's fundamental as we go on. So every G set can be decomposed as a disjoint union of transitive G sets. So the building blocks for G sets are transitive G sets. Whoa. Transitive G sets. And you learn in algebra class that transitive G sets are always of the form G mod H for some subgroup of G. And in fact, uh, G mod H is isomorphic to G mod K if and only if H and K are conjugate subgroups of G. And so this tells us that just like in the representation ring case, the Burnside ring has a canonical basis additively. So additively, A of G is the free abelian group on the isoclasses of transitive G sets. And we understand what these look like. So we have a canonical basis again. And I just want to say this one other way, which I find helpful. So in other words, if I let conj of G be the conjugacy classes of subgroups of G. So conj of G as opposed to G mod conj, which we used previously to denote conjugacy classes of elements in G. This time this is conj of G is conjugacy classes of subgroups of G. Then we can write A of G as the direct sum over conjugacy classes of subgroups of G of Z supported on the isomorphism class of G mod H. Whoa. Of G mod H as a G set. So there it is. So these transitive G sets are playing the role of irreducible representations. So additively, this ring is quite simple, but we'd like to understand it multiplicatively. And in this case, you can do a little bit better than you can do in the representation ring case, actually. At least it requires less technology to make the following statement. So to understand the multiplicative structure, well, what do we need? We need to understand how G mod H times G mod K decomposes into transitive G sets. And here G is acting diagonally, right? G is acting diagonally. And this is just something you can figure out yourself. It isn't actually that hard. So it turns out that there's an isomorphism of G sets between G mod H times G mod K and the disjoint union over double cosets. So let's call this H little g k in here of G mod, I'm going to conjugate little h by G. So that's what that notation means. I'm going to intersect it with K. Don't ask me right now if conjugation means GHG inverse or G inverse HG. Don't ask me. And this is an isomorphism as G sets. Uh, so that's great. So this tells us that if we want to understand the product of two basis elements in this ring, we just need to understand what's going on the right-hand side here, which is not an easy thing to understand. At least we have a formula for it, but it's not really an easy thing to understand because not only are double cosets showing up, but an intersection of two subgroups in a group is a kind of hard thing to calculate. But let's do an example. So just like in the representation ring case, the Burnside ring of the trivial group is the integers because it's the growth and decay ring of isomorphism classes of finite sets in that case. But let's let's consider the next most interesting example, which is the Burnside ring of the cyclic group of order P. So in this case, we have two isomorphism classes of transitives, and these are CP mod CP, otherwise known as 1 in the ring. And the other one is CP mod E. This is our new thing, and we'll call this X. And we want to know how to square X to give a presentation for this ring. And well, we just need to understand CP mod E times CP mod E, which you can understand lots of ways. So in particular, CP mod E is a free CP set. When you cross any G set with a free G set, you get a free G set, a disjoint union of free G sets. So um, so uh, or we could use this double coset formula up here, which tells us that this is the disjoint union over CP mod E of CP mod E. And that's a disjoint union over P things of CP mod E. And so we learn that X squared is PX. And so the Burnside ring of CP is isomorphic to Z adjoint X mod X squared minus PX. In particular, it's rank 2. And that is in contrast to the representation ring case, in which case the rank of the representation ring of CP was P. And there is a close relationship between Burnside rings and representation rings. There's a linearization map, which is going to come up a few times today because I just want to continue to explain how all of these things are related to each other. So the linearization map I'm going to call L, and this goes from A of G to RU of G. And it is induced by the map taking a G set X to the G representation that I get by taking the free complex vector space on X and then letting G act on the basis the way that it acts. Um, and this sends coproduct to direct sum and product to tensor product. So this is a ring map. We know what the map from A of CP to RU of CP does because previously um, we calculated what the representation was that's C on CP mod E in the representation ring of CP. It's the sum 1 plus x squared plus x cubed up to x to the p minus 1. And so in the case that in the case that we're working with A of CP, what happened here? There we go. We see that A of CP injects into the representation ring of CP. So this map L is definitely not necessarily an isomorphism. In fact, it's very rarely an isomorphism, but it's also not necessarily injective because we could consider the case of C2 times C2, the Klein 4 group. So not necessarily injective or surjective. So just consider G equals C2 times C2. So what happens here, in the case of C2 times C2, the Burnside ring of C2 times C2, well, it's a free Z module of rank equal to the number of subgroups of C2 times C2. There are 5 subgroups of C2 times C2. And the representation ring of C2 times C2 has rank 4 because there's 4 conjugacy classes of elements in C2 times C2. And so the map L must not be injective in that case. And it is a fun exercise, which I will give you to try and write down an element in the kernel of this map. That's a fun exercise. So write down an element in the kernel of this map in the case of the Klein 4 group. Okay. Are there any questions at this point? So I want to talk about restriction and transfers. I'm not going to say a lot. So if I have some map, uh, phi from H to G, well, then I get a restriction map along phi from A of G to A of H. This is exactly the same kind of thing as happens in the representation ring case. I just use phi to have H act on X, and this is a ring map. There's also a transfer map along phi for arbitrary phi from A of H to A of G. And let me say how that works. So here, if I have an H set X, I'm going to do something very similar to what happens in the representation ring case. So there's a kind of Borel construction that I form. So I form a G set, which I'm going to call G times over H with X, with a little phi there to tell me how H sits inside of or maps to G. And what is this thing? So this is the quotient of G times X by the relation that G comma HX is related to G phi of HX. So it's a kind of Borel construction or co-equalizer. And that's the transfer map. This is additive as before. And I'm going to do some examples of this transfer map, but I do want to just state that these, let's see if I can do this. So this structure here, this satisfies the double coset formula. And Frobenius reciprocity. So this endows the Burnside ring with the structure of a global green functor, And in fact, the Burnside ring global green functor is the initial global green functor. This is a good exercise. In fact, I'm going to give you the key thing that you need to prove this in just a second. But it's a fun exercise to actually check that the Burnside ring global green functor is the initial global green functor. It's not too shocking because it's coming out of the equivariant sphere spectrum, which is the initial uh, equivariant commutative algebra in equivariant spectra. Um, so uh, so let's talk about these transfers. So if H is contained in G, then the transfer from H to G of a basis element, which looks like H mod K, is, well, this thing, G times H with H mod K, which you will not be shocked to learn is G mod K. And so the transfers here send basis elements to basis elements. So the transfers along injections sends basis elements to basis elements. This is a big difference between the Burnside ring and the representation ring. And this is a thing that's really helpful in trying to prove that the Burnside ring is the initial global green functor. This is the thing that sort of allows you to do an inductive proof of this. So you can just I'm going to leave it at that. So these transfer maps are really nice, but transfers along surjections, I want to do that one too, for one surjection. So let's consider G to the trivial group. Okay. So this is an important one. This is like always an important one when you have transfers along surjections. And so if I transfer from G to the trivial group, some G set X, well, what happens? This is E times over G with X, and that exactly quotients out by the G action. So this is the E set X mod G, which is just being captured by the cardinality of X mod G. So this is in A of E, i.e., the transfer from G to E is just counting the number of G orbits in X. That's all that it's doing. It's just counting the number of G orbits. And this is going to be important in a little bit. Does that make sense? Are there any questions? Okay. Because we have restriction maps, we have an external multiplication map or Kunith map induced by the restrictions. So this is just defined exactly the same way as in the Burnside ring case. It goes from A of G, tensor A of H, to A of G times H. And it takes a G set X and an H set Y to the G times H set X times Y. But unlike the representation ring case, this is not generally an isomorphism. And it kind of fails again immediately in the first place it could, which is with the Klein 4 group. So in the case of the Klein 4 group, the left-hand side has rank 4 and the right-hand side has rank 5. So it fails immediately. It is actually an isomorphism kind of more often than you'd think. If G and H have relatively prime orders, then it turns out that this is an isomorphism. And that might be an if and only if. I'm actually not sure. But I think it's pretty rare for this to be an isomorphism. Maybe I should write here. Consider C2 times C2. Okay, so that brings us to the next big topic, which is character theory. And it turns out that these Burnside rings admit character maps, while that are extremely well behaved. Um, just like in the representation ring case, and we can use these to get a better understanding of these Burnside rings. This is the way we understand them in general, is through character theory. And so in this case, the thing that's going to play the role of conjugacy classes of elements in G is conjugacy classes of subgroups in G. And so our version of class functions, I'm going to call marks. So let's let marks of G comma Z be the ring of functions from conjugacy classes of subgroups of G into the integers. People use lots of different names for this ring. Some people call it the ghost ring. Some people call it superclass functions or supercentral class functions. Um, Superclass functions makes this ring sound complicated to me, and the ghost ring makes it sound mysterious to me. And I think it's neither of those things. And so I go with a very simple name, which is marks, which is comes from the when people first messed around with this thing, they just called if I took in a G set and I took the fixed points and I counted how many there were, they called it the table of marks, and so I just call it marks. So this is probably just on me. But I don't really love those other two names. Uh, so what's the character map do? So this goes from the Burnside ring of G to this ring of marks. And it does this very simple thing where if I have some G set X, what I'm going to do, so it goes to chi of X, and I'm going to evaluate this on some conjugacy class of subgroups in G, and I need to get out an integer, and that integer is just the order of the fixed points for the H action on X. And this fixed points is an extremely well-behaved construction. And so this turns out to be an injective ring map. And if we rationalize this map, and rationally, it turns out to be an isomorphism. So this is in many ways much simpler than the representation ring case because the coefficients are just the integers or the rationals in our character map. So it lands in the functions on conjugacy classes of subgroups taking values in the integers. And if I rationalize chi, I get an isomorphism. So there's no roots of unity that you have to mess with, like in the representation ring case. Does it make sense? Okay. So once again, you can ask for formulas for restriction and transfer on the level of marks compatible with the restrictions and transfers on Burnside rings. And this is doable. Restrictions and transfers on marks. So for restrictions, it's just the exact same kind of thing. If I have a phi, it induces a map on conjugacy classes subgroups, and I just use it to restrict. So I'm not going to say anything about restrictions. I am going to say some stuff about transfers, though, because here the story gets surprisingly interesting. So first of all, for H contained in G, for transfers along injections, it is very similar to class functions, similar to the RU story. And the formula looks just like what you would expect. So it's like TR H G F on K is equal to the sum over GH in G mod H, such that the conjugate of K is contained in H of the value of F on the conjugate. So that's really the same kind of thing as happens in the representation ring story. But for surjections, in the representation ring story, we gave a very nice formula for the transfer along a surjection. And the Burnside ring story is just enormously more interesting. So for surjections, the story is interesting. And let me just try to say a word about why that's the case. So there's a thing you can do. Of course, there's a formula on the level of marks, at least with rational coefficients, for the transfer along a surjection. Why do I know that's true? It's true because I can rationalize chi. That's an isomorphism. I can invert the matrix, do the transfer on the Burnside ring, and go back down through chi. And I can just trace through the formula for that. And that's some formula. And Serge Buch does this. This is essentially how he comes up with a formula for a transfer along a surjection in his book on bisets. So he has a big book, and this is one of the things that he does in there. But the formula is pretty complicated because it involves inverting a matrix. And there's sort of hope that you might be able to come up with a more elegant formula. And the reason there's hope is because in one case, there's an extremely elegant formula. And that's the case for the transfer from G to the trivial group. So if I have some element in marks of G, and I'm interested in the transfer from G to E, there's only one thing I can evaluate it on. The formula for this, well, what am I doing? I'm up on the level of the Burnside rings. I'm counting the number of orbits for the G action on X. And so that tells me that the formula here should be 1 over the order of G times the sum over G and G of the value of F on the conjugacy class of the subgroup generated by little g. Why do I know this? Well, this is Burnside's lemma. So this is Burnside's orbit counting lemma. And this is not the formula. This is nowhere close to looking like the formula that you get if you invert the matrix and calculate the formula that way. It's like really hard to see that that's the same as this formula. So, uh, so in this case, there's this very elegant formula for the transfer along a surjection, and you could wonder, are there other surjections for which there's an elegant formula of this sort? Okay. So somehow the story for transfers along surjections I find very interesting, and I think there's deep connections between it and, finite group theory and combinatorics because of this thing about trying to generalize Burnside's lemma. Um, and one more thing that I want to say about formulas for restriction and transfer on marks is that these are compatible with the formulas for restriction and transfer on class functions because there's a version of L for marks. So I can go from marks of G comma Z to class functions on G, taking values in Q adjoin mu infinity. And I'm just going to continue to call this L. It's going to be compatible with the map L from the Burnside ring to the representation ring of G. And the formula for L is that if I evaluate L on an element in marks F, and then I evaluate this on a conjugacy class of little g, then I get F of the subgroup, the conjugacy class of the subgroup generated by little g. So that's exactly what you would hope for if you tried to write down a formula like this, and that turns out to be the right thing. And then all of this is compatible with the map L from the Burnside ring to the representation ring, and for all the formulas for restrictions and transfer maps and stuff like this. Okay, so I'll write compatible with restriction and transfer. Okay, my next goal is to go on to power operations. Are there any questions at this point?
So the Gawa action of the image is trivial.
Yeah.
That's cool. Is the is what happened with the symmetric group an artifact of this?
Well, let me think about this for a second. You're asking if this lands in the z hat fixed points. Is that true? Or the z hat times fixed points? Yeah, I think. Yeah, I think that's true. Yeah, I think that's true.
Mm.
Um, the symmetric group question is a good question. So it turns out that the map from the Burnside ring of the symmetric group to the representation ring of the symmetric group is surjective. And so that is going to be closely related to these things. And this is worth sitting around and sitting down and messing around with. Yeah. Okay. Yeah, great. Any other questions? Power operations then. So the definition of the power operation is very similar. So it's the map from A of G to A of G Reth sigma M. And it's induced by the following operation. If I have a G set X, what I want to do is raise it to the mth power and view this as a G Reth sigma M set. And you run into the exact same issues previously. This is not an additive operation, but the failure of additivity is exactly these transfers that we talked about before. The power operations satisfy exactly the same list of axioms that I have up above in this document that I could just scroll up to, but it would make us all seasick. And uh, uh, So in that sense, everything looks like it's kind of the same as the representation ring case. But actually, here is where the story diverges in a large way. And that's what I want to try and explain with the rest of my time today. So first of all, something special happens. And that's that if I consider the power operation on a basis element in the source, well, what am I doing? We know that this is G mod H to the M as a G Re sigma M set. But it turns out that G mod H to the M is isomorphic to G Re sigma M mod H Re sigma M as G Re sigma M sets. And so the total power operation is sending basis elements to basis elements. Um, and this gives you a lot of control over what's going on in this case. And I want to sort of try and get a more in-depth understanding of what's going on by looking at the case of the trivial group. So let's just consider the trivial group for a second. So in this case, our power operation PM goes from Z to A of sigma M. 0 goes to 0. 1, which is E mod E, goes to sigma M mod sigma M, which is 1 on this side. And then things get interesting because we have to deal with the fact that we have to deal with the way that power operations interact with the additive structure. 2, it turns out, big surprise, is 1 plus 1. And so what's this go to? Well, it goes to the sum over I plus j equals m of the transfer from sigma I times sigma j to sigma m of, well, the external product of pi on 1 with pj on 1. And that's sigma I times sigma j mod sigma I times sigma j. So the external product, right? The pi on 1 is sigma I mod sigma I. P j on 1 is sigma j mod sigma j. And when I external the product those together, I just get this trivial thing, sigma I times sigma j mod sigma I times sigma j. So why am I talking about this? Well, because the transfer is interesting. So what we get here is the sum over I plus j equals m of sigma m mod sigma I times sigma j. And this one calculation suggests that something strange is going on When I apply the power operation to a G set, only certain kinds of subgroups in the symmetric groups are arising in the target of the power operation. Sigma I times sigma j is not an arbitrary subgroup of the symmetric group. Sigma m has lots of subgroups. Sigma I times sigma j is a very special subgroup of the symmetric group. So continuing, we see that elements in the image of PM are built out of sigma m sets of the form sigma m mod sigma lambda, where lambda is a partition of m, an integer partition of m. Let's just remember that that means that the sum over I of lambda I times I equals m. Lambda sub I is always counting the number of times I occurs in my integer partition. And what I mean by sigma lambda is what you would guess. It's the product over I of sigma I to the lambda I. This is the kind of thing, this is exactly the kind of thing that we're seeing in this case. Uh, and these are very special conjugacy classes of subgroups in the symmetric group. These are called, or even very special subgroups of the symmetric group. These are called the Young subgroups of the symmetric group.
Can I ask you a question about these partitions, or should I ask you after class?
No, you can ask me.
Uh, so, does your notion of partition, is it the same as, is it equivalent to the standard notion of a partition?
Yeah.
So, like when you're talking about the symmetric group, like it's still true that partitions correspond to conjugacy classes.
Yeah. Yeah.
Um,
Yeah. I'm just counting the number of times I occurs in my integer partition. So if I have 1 plus 1 plus 2 equals 4, then lambda sub 1 is 2 and lambda sub 2 is 1. If I have 1 plus 1 plus 3 equals 5, then
yeah,
lambda sub 1 is 2 and lambda sub 3 is 1, but lambda sub 2 is 0. It's just counting how many times the number occurs in the integer partition.
I see. Maybe I'll ask you more about that out of class.
Okay. So this suggests the following thing. It suggests that somehow the image of the total power operation is smaller than you would expect it to be. And this is very different from the representation ring case. Somehow in the representation ring case, like if you're thinking about representations of the symmetric group, if you're thinking about the map from Z to the representation ring of the symmetric group given by the power operation, well, you only see partition information in the representation ring of the symmetric group, right? That's the only information that's there because partitions correspond to conjugacy classes of elements in the symmetric group. But here there's tons of subgroups in the symmetric group, but it turns out only the ones corresponding to partitions are showing up in the image of the power operation. So this suggests the following definition. So let's let uh, angstrom, this is just some notation of G comma N contained in A of G re sigma M be the span of the smallest collection of basis elements in the canonical basis for the Burnside ring of G re sigma M such that the span contains the image of PM. So I'm just going to only consider the summand of A of G re sigma M in the canonical basis that contains the image of the total power operation. And like what I've tried to do is convince you that that's smaller than all of the Burnside ring of G re sigma M, which I think this thing above at least is convincing that that's the case for the G trivial. But what I'd like to do is tell you a bunch of equivalent constructions of angst of this subgroup of A of G Reeth sigma M now. So this is what we're going to try and focus on for the rest of our time, because I think this is a place where there's a big divergence, and I think it's cool. So equivalent constructions of angstrom of G comma M. And I've got three, but I don't know how many we're going to get through. But let's start with this one. Um, so it turns out that angstrom of G comma N is a Grothendieck ring. And so that's the first thing that I'm going to explain. So what's it a Grothendieck ring of? Well, a G Reeth sigma M set X is called submissive if X injects into Y to the M for some, and this has to be a map of G Reeth sigma M sets for some G set Y. So if I can embed X as a G Reeth sigma M set in Y to the M for some G set Y, then I call X submissive because it submits to power. That's why it's called submissive. And it turns out that submissive G Reeth sigma M sets are closed under, oh, that was the D, closed under disjoint union and product. Product is clear. If I have two submissives, X and X prime, then X times X prime embeds in Y times Y prime to the M. And disjoint union is also pretty easy. If I take the disjoint union of X and X prime, well, this embeds in Y, disjoint union Y prime to the M. If X embedded into Y to the M and X prime embedded into Y prime to the M, then X disjoint union X prime embeds as a G Reeth sigma M set into Y disjoint union Y prime to the M. And so since these G Reeth sigma M sets are closed under disjoint union and product, I can form the Grothendieck ring. So here's our fact. Angstrom of G comma M is the Grothendieck ring of isomorphism classes of submissive G Reeth sigma M sets. And this is just not that hard to see. It's a good exercise to try and do this. You just need to show the two inclusions. So that the Grothendieck ring of submissive G Reeth sigma M sets is contained in angstrom and vice versa. And the argument is not hard, which I should do one of them. So if I want to show the Grothendieck ring of submissives is contained in angstrom, well, if X sits inside of Y to the M for some Y, then any basis element, if I decompose X into transitives, any one of those transitives sits inside of X, sits inside of Y to the M, and so that transitive is used in decomposing PM of Y inside of A of G into basis elements. And so that's the proof of that direction. And the other direction is very similar. So this is kind of how this goes. But we learn things from this. So first of all, we learn that angstrom of G comma M is in fact a subring of A of G Reeth sigma M. And it's a Grothendieck ring. Okay. So I want to give another description. Yes, this one's fun. So my goal here is to connect with our formula for the power operation on class functions from last time. So let's let parts of G comma M be the set of conj of G decorated partitions, integer partitions of M. So what is such a thing? Let's remember that such a thing is a map lambda from the set of conjugacy classes of subgroups of G times n greater than 0 to n with the property that if I sum over all pairs where I take a conjugacy class of subgroups and a positive natural number I of the value of lambda on the pair times I get M. Then there's a map, which I'm going to just call alpha, from parts of G comma M to conj of G Reith sigma M. So associated to a conj of G decorated integer partition is a conjugacy class of subgroups. And how am I going to do it? Well, if I have some lambda, I'm just going to send it to the conjugacy class where I take the product over H comma I of H Reith sigma I to the lambda H comma I. And in the case that G is trivial, this should already look interesting because in the case that G is trivial, we're using integer partitions to pick out the Young subgroups of the symmetric group. And that can be generalized to an arbitrary G using this notion of a conj of G decorated integer partition. And it is a fact that I'll get into if I have a little bit of time at the end, that alpha admits a canonical, okay, you're getting it, good. A canonical, canonical retract, which I call beta. And that is a little bit hard to describe. The idea is that if I have an H contained in G Reith sigma M, I want to get out one of these decorated partitions. And this is a mouthful. So first I have an H set M coming from the surjection from G Reith sigma M to sigma M. And I can decompose that into transitives. And that gives me an integer partition. But I want to decorate that integer partition. And so if I have H sitting inside of G Reith sigma I, and it's sitting transitively in the symmetric group part, or the map from H to sigma I is transitive, then I can pick an element in the underlying set of that sigma I axon, and I can take the stabilizer for that, and that's a subgroup of H. And then what I'm going to do is, and that stabilizer sits in the stabilizer of G Reith sigma I acting on that thing, which is a product of G with G Reith sigma I minus 1. And then I can take the map from the stabilizer in H to G times G Reith sigma I minus 1 and project onto the G. And the image in there is a subgroup of G that is actually well defined up to conjugacy. And that's how I decorate my partition. Okay, that was incomprehensible. I apologize. I also apologize to all future people watching this video. Okay, so alpha admits a canonical retract beta. It's a bit hard to describe, but now there's a game that can be played. So let's let parks of G comma M be integer valued functions on parts of G comma M. The idea is that I want to replace, I prefer to work with these partitions of M decorated by conj of G than arbitrary subgroups of G raised sigma M. And so I'm just going to use a different ring than Marx. I'm going to use this ring, Parks, which has combinatorial things that go into it. So it's a little bit easier to work with. And then there's the character map for A of G wreath sigma M. So this lands in Marx of G wreath sigma M, taking values in the integers. But the map beta induces a map from Parks of G comma M to Marx. So that retract, it goes the other way, and so it induces a map this direction on Parks. And it turns out that angstrom of G comma M is the pullback. So there we go. There's another description of angstrom of G comma M. It's this pullback, and this equips us with a character map for angstrom of G comma M. So this special subring of A of G wreath sigma M also has character theory, and that character map lands in something more combinatorial than the character map for the Burnside ring of G wreath sigma M. And this allows us to give a formula for the power operation for Burnside rings on the level of Marx. So we win something big here, which is, well, what do we know? Well, we have the power operation. Of course, this lands in A of G wreath sigma M, but by construction, it lands in angstrom of G comma M, sitting inside of A of G wreath sigma M. And then we have our character maps, which I'm just going to get rid of the integers and just write Marx and Parks. Whoop, this one doesn't exist yet. Parks of G comma M. Marx of G wreath sigma M. This is beta star. And what you would like is you would like a formula down here. Maybe I'll call this PM Marx. From Marx of G to Parks of G comma M. And this is not hard to write down now because on this side, we have this very combinatorial basis. And we can write down a formula just like before. So PM Marx of F on one of these partitions of M decorated by conjugacy classes of subgroups of G is the product over H comma I of the value of F on H to the lambda H comma I. And that works. That is the formula for the power operation. And so the trick here was like, rather than trying to give a formula that goes the whole way over here, which is tricky because somehow you have to combat two things at the same time. The fact that you want some kind of combinatorial thing, but the fact that subgroups of G wreath sigma M aren't particularly combinatorial in nature. The trick is to understand that PM lands in a small subring of A of G wreath sigma M. This is enormously smaller than this in general, because of course there's lots of conjugacy classes of subgroups and symmetric groups. Notice that that thing has its own character theory, which is very combinatorial in nature. And then this allows you to actually give the formula that you know you want to give for the power operation on the level of Marx. Okay, I had more to say, but I think hopefully what I've tried to do is focus on aspects of Burnside rings that are very different from representation rings, and I think this is a very important difference. And so I've tried to explain it. Okay, I'm going to stop there.
All right, let's all thank Nat for the lecture.